Hi, welcome back. This is the second episode of building Pixie. So, in the last video, I was talking about the architecture of Pixie, what kind of a machine it is, and then I mentioned in this episode we'll start building an assembler for Pixie. So, that's what we are going to do today. We'll start building it. We'll see how much progress we can make today and then continue again in the next episode. So if I go back to the specification that we saw earlier, we covered most of the things in this section 2. One thing we should look at today is the instruction format for Pixie. So any instruction, we briefly saw the add instruction last time, but this is a much more general description. So any instruction, any assembly language instruction in Pixie has an opcode which specifies what kind of operation we are doing, and 0 to 3 operands. So there could be a destination operand which stores the result of an operation, and possibly 0, 1 or 2 source operands. There may not be any operands at all, that is also possible. But if these operands are present, the order in which they are arranged is the destination operand first and then the source operands, and these will be comma separated. So for example, if I just scroll down, you can see add destination operand and then the 2 source operands. So this is a format of this. And there are different types of operands possible. So we could have an operand located in a register. So then in the instruction, you will see them denoted as SR or DR or SR1, SR2, and so on. So SR is a source register and DR is the destination register. There are some cases where the instruction itself contains the value to be used as the operand. So instead of putting the value into a register and then operating on it, the instruction itself contains the value of the operand, and the value could have different sizes. So they are represented by these immediate operands, which could have 5 bits, 6 bits, 8 bits, or 16 bits in size. So you will see these in a bunch of instructions. There are also some instructions which operate on an address. Since addresses are 20-bit, you will find them as ADDR20, address 20 in the instruction. This is also very similar to immediate operand, but in this case it's an address. Then we also have register indirect operands. What this means is the operand is located in a memory location, and the address of that memory location is stored in a register in the lower 20 bits of that register. So remember, registers are 32 bits, but the lower 20 bits will contain the address. So in that case, we put the register within square brackets, indicating that this is used as an indirect operand. There is also a case where we can use register indirect addressing, but with an index. This is useful if you have an array and then you want to index into a specific element in the array. So the base address of the array will be stored in one register and the index will be stored in a second register. So in that case, it's represented with a pair of registers, and we will write it like SR1 plus SR2, but within square brackets, or DR1 plus DR2 in case it's a destination register. So again, there are various ways in which this is encoded and so on, which we probably will not take a look at today. But when we build the assembler, and eventually when we have to generate the machine language code, then we need to know how these are encoded in machine language. But today we are more interested in the syntax, and then how do we parse the assembly language program. Okay, so let's get started. By the way, the project page link is given in the description. You can clone this. I have already cloned this, so you can see this here. I have already cloned. Whatever is in the repo is what I currently have. So we'll get started. We'll get started. So let's go here. This is our README. So nothing much here. So what I will do is I'll keep track of our project status. So we discussed in the last episode that we will first build an assembler, then we will build the VM itself, and eventually the operating system, maybe with device drivers. We'll get to it when we reach there. So this is what we want to do. So today we are going to start building a parser which will read the source code or the assembly language code and then convert this into a abstract syntax tree. So abstract syntax tree is nothing but a data structure which represents these instructions and the entire program that we have. So that's what we will start today. And then after this, maybe we will look at how to generate the machine language code, so code generator. And then of course there might be other components. We'll see that. So today our focus is going to be just the parser. Okay. So if you're slightly new to Haskell, there are various build tools that one could use. I'm going to use a tool called Stack. If you don't have, you should install it. There are other tools available, but for this project I'm going to use Stack. So Stack has a bunch of files, a few files. So first one is called stack.yaml. We'll start there. So the concept of Stack is a build tool. It's a package manager, sort of, right? It basically manages the dependencies that you have in your project with other libraries or components and so on. And it sort of guarantees reproducible builds by using this concept of resolvers. So what is a resolver? Resolver is nothing but a set of packages that are known to work with each other. In the sense, you can compile them together. There won't be any compilation errors. All these specific versions of packages are compatible with each other. And Stack also, a specific resolver also ensures that all the tests of these packages, all the tests pass when you compile them together. So it's like a known good configuration of packages. So let me show you an example. So if I go to the browser and let's look at Stackage. So Stackage is the repository in which these specific resolvers and package versions, everything can be found. So there are these nightly resolvers and there is also LTS resolvers. I'm going to use LTS. So the latest LTS seems to be LTS 17.5, and then when I created this it was 17.2. Maybe we'll go to the latest LTS version. So let me open it up. So you can see there are a bunch of packages in this LTS 17.5 and various versions of these, right? And all these versions are known to work together. So we will go to this latest version of LTS, which is 17.5. I'll modify this, and just to make sure everything is still working fine, let me come back here and wait. Okay, everything seems to be fine. Now we will edit the Pixie package. Now that is done by editing this package.yaml file. Again, this is a skeleton that I generated. You can generate a project skeleton by running stack new command. I have generated something with some defaults. So we'll go line by line. We'll look at it. The first section is mostly about the project location, some description, some details, and so on. So we'll ignore that. The dependencies, so there are various components inside one package. The dependencies that you see here at line number 14 is the dependencies that are used by every component inside Pixie. So right now I have two components. There is something called base, which is by default included in almost all the libraries that or programs that you will write Haskell. And then there is Relude. Relude is alternative prelude. You are used to the Haskell prelude. It's like a standard library of Haskell with many of the commonly used types and functions and other things included. But there are a lot of shortcomings. So usually people prefer to use your own version of standard library. Relude is a pretty popular one, pretty good one in my opinion. So many of my projects I use Relude. So there are various ways in which you can replace your default prelude, which comes with Haskell, which comes with GHC, and substitute Relude instead. I'm using one mechanism here. There are other ways of doing this. You can go and check out the Relude documentation. I'm using this approach where you add an extension called no implicit prelude. This will remove the default prelude from compilation and then include Relude. I will explain why I prefer this approach. Of course, this is not the only way of doing this, or may not be the optimal way of doing it in some other project, but in this project I want to use it this way. I'm also using this other extension called overloaded strings so that I can make use of string-like types, literals of string-like types like text or byte string and so on. And then a bunch of warnings are enabled by default so that I can catch some obvious mistakes. So with that out of our way, my bad, I don't think I was sharing Emacs. Okay, so let me show you this again. So mostly the first section, the top section that you see here in Emacs has the description and other details of the project. And I also talked about how I'm using Prelude with this default extension called no implicit prelude. Right? So no implicit prelude will remove the default prelude from while we are compiling our source code. And then I'm including prelude. Now, I also use this overloaded string, which I explained, because I want to use some string literals in code, but the type of that literal may not be a string. It might be a text or a byte string. So in Haskell, by default, if you include a string literal, it has type string. This is a way to overload that, and then it can mean either a string, it can mean a text, or any other type which has an instance of isString class. So we'll see some usages of this while we start writing code. And then I have enabled a bunch of warning flags to that we pass to the compiler. So next we look at the components of the package itself. So any Haskell package can have a library component. We can have only one. Any number of executable components, any number of test components, and there are a few others also if you're doing performance benchmarks and so on. But right now we'll start with one library component, which is located in the lib directory. And then since we are building only an assembler, I'm going to call it PASM, Pixie assembler. So the executable that we are going to compile will be called PASM. And then I have one test component here for testing this assembler, PASM test. So the main function is located in this main.hs under PASM/app. So let me show this. Okay, we'll import this. You can see that I have an import prelude and then a main which is not doing anything at this moment. This is just a skeleton. Now I will tell you why I am doing it this way. So there are various ways of including prelude into your project. I prefer this one because it's pretty explicit. That is one reason. So it's very clear that we are removing the default prelude here and explicitly including prelude. So in a public project, I think this is a good idea because other ways of including prelude involve modifying either this package YAML file or some global package configuration file. It's not visible in the source file. You may not have this import line here. So if I follow those approaches, which you will find in the prelude documentation, I have seen two problems. One is sometime back, some of the tools that I use for formatting source code, for example, stylish Haskell that I used to have trouble if I use some of the other features like cabal mixins and so on. Maybe those are no longer applicable. I haven't checked recently. So that's one reason, but more importantly, keeping an import statement here makes it very clear that we are using prelude and not any other random prelude or the default prelude that comes with GHC. So this is being an explicitly notated import statement. It's very easy for the readers to figure out what's going on. That's one reason I prefer this. Okay, so this is the main function, the main module. but the actual code, most of the code that we write, we will write in this library, which is located under lib, and I don't have anything right there. We will write something today. So then what happens is when we compile the package, first the library gets built. You might have already seen when I compiled it here. So you can see that the library first gets built. This pixie 0.1.0.0, that's the library. And then the executable gets built by compiling the main. So since library doesn't have anything, you don't see it compiling anything at all. Then later the main gets built. There you can see the thing. Similarly, if I want to run the test, so you can, one thing you should see is the executable contains a dependency with Pixie. If you go back to the package YAML, there is a dependency to Pixie from the executable because Pixie is a library. Similarly, the test also has a dependency with Pixie. So you can write tests against the library. So we will have very minimal code in the main itself. Practically all the code that we write will be in the library. That's what we are going to do. Okay, so now with that, let's get started. So first, we already have the ReLute dependency here. We need to figure out how to parse the source code. So there is a pretty good parsing library called Megaparsec. I'm going to use that one today. We'll add the dependency to Megaparsec. And let me confirm that we have Megaparsec. Yeah. So LTS 17.5 has Megaparsec 9.0.1, and I will explain some parts of this, but may not be everything. Megaparsec is a parsing library, so it can read your source code and then convert this into an AST by parsing. And we will see a technique called Parser combinators. This library is a Parser combinator library. We will figure out what is this and then how is it useful. This is one of the strengths of Haskell, that you can write smaller parsers parsing one particular piece of your source code and then combine many such smaller parsers to create one big parser. This technique is used in many of these parser combinator libraries, so we will see that. But before that, first let's figure out if we parse the source code. So let's go back to the specification. If I parse an instruction like this and produce an AST, what does that AST look like? That's what we want to see, right? So let's start building that AST. So I will go back to this. I have the specification here, so maybe I can open that right here. I don't need to. Let me go back to Emacs and let's see the spec. Okay. So we are interested in the instructions. So these are the instructions that we want to pass. So let me start. Remember, the library is in the lib directory. We will create Pixie assembler. Should I call it ASM? Should I call it something else? Maybe ASM is good enough. I don't know. Yeah, we'll go with ASM. Let's see. So Pixie lib Pixie ASM parser. Pixie. So what do we need? We will import ReLute, and we need a new data type, which is the syntax tree for any instruction. So we'll call this instruction. And like I was saying, any instruction has an opcode and some operands. So if you look at the add instruction, there are two encodings for add. So we will represent it with this op add, and then it has a destination register, a source register, and then last argument is either another source register, or it is an immediate 16 value. This is how you can represent that in Haskell. And usually most of these data types that I come up with, I try to make it easy for debugging with this show any cute derivation. So we obviously didn't say what is a register. So a register, we know that it's 32-bit value. So we can say new type register, which is a register with a word 32. Now here I'm a little bit confused whether it should be a word or whether it should be an int 32. Maybe it should be an int 32, because some of these operations that we are going to do, for example, this addition itself, it's integer addition, it's not a unsigned integer addition. So maybe we'll start with int 32 and then we'll see. So again, I'll derive show and keep. I also prefer to give this deriving strategy here. So we need to add, if you're not familiar with this, don't worry much. What this means is there are various types of derivations. If you don't specify which one you're using, then it's called the stock deriving strategy. So, okay, so let me build it one time so that Haskell language server is happy. Maybe it didn't like because I changed the. Okay, we will continue defining these immediate values. So now you need immediate 16. So again, for now, I will go with an int 16. We'll see if we want to change this. Okay, great. Now, if you look at subtraction instruction, it's pretty similar to this. There is no difference. Let's see. Exactly the same. I'll just use the same set of constructor parameters. Multiplication is the next one. That's interesting because if I remember correctly, there are a number of encodings. So So it multiplies, and there are three variants. There is a byte variant, short variant, and word variant, which is mul B, mul C, mul V, which is operating on byte, short, and word. Similarly, there are unsigned variants as well. So there are a total of 6 distinct variants, but all of them have 3 operands, which are registers. So I will say op or just 3 registers. And this is a short, this is the word. Now we need a same thing, but this time for the unsigned variant. I believe I got that right. Then negation, 2's complement negation is the next one. That just takes 2 registers. Next is comparison. Comparison again is straightforward. So the first argument is always a register. Second one is either a register or it's an immediate 16 value. So straightforward. Then we have logical AND. Again, similar to our addition or subtraction in terms of operands. So I will just copy paste that. And logical OR, I believe, should be similar. Yep. NOT, which is a bitwise complement. To registers. XOR should be similar to AND or OR. Bit shift. Interesting. So there are many variants of this. There could be a left shift or a right shift, and right shift has 2 variants, either logical right shift or an arithmetic right shift. Okay, so the left shift is 2 registers followed by either a source register or immediate 5 operand. The same thing in the other 2 as well. So it's just a matter of shift left, which has 2 registers, and it's not immediate 16, it's immediate 5. We follow this convention. And then we have a right shift with 0 filling, or a right, which is like a logical right shift, and a arithmetic right shift. Now, of course, we don't have immediate 5. Now this is a little bit interesting because there is no 5-bit native data type in Haskell. So the closest what we have is a word 8 or an int 8. I'll use int 8 and we will get back to this. This is an interesting case. Okay, that is sorted out. Next is jump, conditional jump. So conditional jump is an interesting instruction. It's probably one of the most complicated ones. There are so many different variants, but they just fall into 3 categories. It takes a single operand, which is an address, and you can specify an address in 3 different ways. Either you can give an address, 20-bit address directly as an immediate operand. So this is ADDR 20. Or you could have a register indirect here. Or you could have a register indirect with an index. We already discussed this. So now in each of these categories, you have so many variants possible. So what this means is there is a JC with a combination of N, P or Z flags. What that means is it'll jump in case you see the N flag, that means it'll jump if it is a negative number, I think. And if it is a P, that means it'll jump to that address, whatever is the operand address. If it is a positive, if it is Z, it'll jump on 0. And NP means it'll jump on negative or positive. That is non-zero value. Similarly, this is like non-positive value. This is non-negative value. And this is always jump. NZP means always jump. Similarly, JC means never jump. Those are the possible combinations. So how do we represent? We could, yeah, we will just go literally, right? First, let's get a basic data structure, and then if we can think about whether we want to optimize this data. So I will go with op JC. So now there are 3 possibilities to represent the address. So I will define a data type called address, and then address has 3 possibilities. So we will say address uh, 20, and this we are going to use, so we need a 20-bit, and this can be represented with the word 32. Of course, the higher bits will be unused in this case. Or we could have a source register. So this is called register indirect. ADDR so this will be a register, or it's a register indirect with index. This will have 2 registers. So JC takes an address, JCN P Z, and then we have NP, NZ, ZP. So that covers all the combinations. We also have this jump unconditionally, which is same as JC NZP, I guess. I think there is a bug in the spec. So JC NZP will always perform a jump. So jump unconditionally should be same as JC NZP. Yeah. Okay. I think. Yeah, so it's talking about the opcode. JC has a single opcode, and then these NZP are written in a different way, so I won't bother much about it. Okay, I'll leave it as it is. Again, this also has just 3 possible ways of representing. So now, in the generated machine code, there is no difference between jump and JC NZP. I haven't written JC NZP. So this is same as op jump, but we will keep them separate for now while parsing, so that we can have both. Maybe some error messages or something will be better if we have them as separate at this stage. But once we generate the code in the machine language, you cannot distinguish between a jump and JC NZP. Then call a subroutine. Again, it takes an address, so this is straightforward. SCL, system call, that takes a 6-bit immediate value. And we need to define that. Okay, the next one is return. So there are 3 variants, and none of them take any operands. Why? Because ret is to return from a subroutine. If you do a call, then you return from the subroutine. You call a subroutine and you return from the subroutine. Ret I is to return from an interrupt handler, which we discussed. Ret S is to return from a system call. There are subtle variations between these. We will see when we reach the VM implementation. There are some small differences. The operation section explains why these are 3 separate instructions. Now load and store. There are so many variants here, but there is a pattern. So you can see here there is load can work on either a byte, a short, or a word, which is why there is LDB, LDS, and LDW. So 3 variants. And then within each variant, all of them has a destination register, and the source is an address. So that's it. That's the combination. So it's straightforward, in fact. So LDB. With the destination register, source is an address. Similarly, LDS and LDW. And that's load. So load will load a value from the address to the register. Store is the opposite. It'll store the value in a register into the specified address. So it's just the opposite. So STB from an address. Sorry, to an address from a register. CS. Okay, that was not that difficult. Then there's copy, which is just copying a value from one register to another. So there are 3 variants. CPY, and our convention is this. Now I wonder whether I should have kept everything as capital, but we'll go with this. So 2 registers. Then there is also a way to put a immediate value into a register, and then you have this confusion of whether it should be sign extended or should it be an unsigned 0 extended. So CPY is an integer, which means I think it's sign extended, and this is unsigned, so 0 extended. Yeah, perfect. Next one is push and pop. So push can either push an immediate value or a byte, char, or word from a register. So push I is a 16-bit immediate. Push U is also 16-bit immediate. Push B is operating on register. So is push S and W. Pop is hopefully simpler because you can just pop to a register. There is no immediate so pop B or S or W. 3 possibilities are there. Now we are down to the last 4 instructions. The in and out are used to access input and output devices. IO ports. So the in as a destination register and either a source register or an 8-bit immediate value, because there are 256 IO ports. Again, we need to define so interestingly, the only instruction that needs an immediate 8 value is the in and out instruction. So this means this can be a word. This doesn't have to be, because there are no negative values. Similarly, 6-bit, this is only used in system call instruction because there are 64 possible system calls. So this also can be a word. There are no negative numbers here. Not possible. Immediate 5 is used only in case of shift. How many? It's a count of the number of bits to shift. So this also is a word. Yeah, only immediate 16 has to be an integer, I guess. But even there, I'm not sure. We need to relook at it when we start writing the parser, I think. This could be a word if. So for example, or it could be negative. Yeah, it could be negative. We already saw examples where it is negative. So we'll leave it as in 60. We'll come back to it when we implement a parser for each of the instruction. I think that time we'll realize whether we want a signed integer or unsigned integer. I think it should be signed at this point. Same thing with register. That makes sense to be signed integer. But again, right now we are writing only the assembler. Maybe in a VM, this is a lot more important. In assembler, yeah, there are cases, for example, when you have immediate operand, yes, we might want to write a negative literal value, like -10. Add source register, destination register, comma, destination register, comma, source register 1, comma, -10, where you're actually subtracting, it's not addition, but you want to do a negative number addition. So it should be possible. Why not? Okay, so let's get back to the last 3. So output is just output to an IO port is just opposite of input, obviously. So out is either a register or an immediate 8 value, that is a destination, and the source is just a register. Simple enough. Then we have SSSP. This is a special instruction. So if you remember that supervisor stack pointer register, I had mentioned the operating system should initialize this register and put a particular value into it so that when we switch to the supervisor mode, it can pick up a good stack. So this is the instruction to load a value into that register, and there are 2 ways in which you can put a value into the register. Either by specifying pop SSSP takes either a 20-bit address or a register. Okay. So now this is a little bit confusing to me. Maybe I didn't think through when I wrote the, why not make it an address operand? Because that's what it is. I think I should modify this. I don't really see any reason not to. There should also be, this should be just a register indirect because that is what it is. Why is it a register operand? It's not a, Oh, it is a register operand because it's saying the value is, yeah, we are not reading from the memory location pointed to by this. Okay, this makes sense. So now this is interesting. We need an ADDR20, right? So the way I had written here, we need to refactor this out. So we'll say new type. We need an ADDR20 type, which is nothing but 32-bit behind the scenes because that's native type. And we need a better name for this. So what I would do this is actually a absolute address, right? So instead of ADDR20, I will call this ADDR absolute. So now I can use either an ADDR20 here or a register. The last one is the halt instruction, which is to stop the computer, and it doesn't take any parameters, obviously. So that's it. This is the entire abstract syntax tree. So our goal is to now write a parser which will read a source program, and if it is a valid source program, valid assembly language program, generate a sequence of instructions where each instruction is one of these. That's it, straightforward. It's not that complicated. And you will see, I don't believe today we have enough time, but I will probably stop here. But in the next episode, when we start writing this parser, you will see that it's very easy in Haskell to write small parsers to parse each of these things, each of these stuff that you see here. For example, we could write a parser to parse a register and a parser to parse an address, and then combine them together and then produce a parser to parse the load B instruction. And then for each of these instructions, we'll write such parsers, and then combine all of them and then produce another parser to parse any instruction. And then you use that to parse an entire program which contains a sequence of instructions. So this is where Haskell really shines, where you can build small things and then combine them and then produce much bigger programs, right? So the composition of smaller pieces to produce a bigger program while giving you a lot of power and a lot of type safety and so on. That's where Haskell really shines. We'll see that in the next episode, where we will actually start using this mega parsec library. And for today, this is it. We just read the spec and then converted that into an AST. We'll stop here today. And as always, if you have questions and comments and suggestions, please feel free to comment. And see you later. Thank you.